Exercise in general grows new neurons, neurogenesis, and promotes new pathways in the brain, neuroplasticity. A study at the Columbia University has shown that moderately to highly trained individuals were able to grow and maintain new neurons in the dentate gyrus of hippocampus at a 2 to 3 times rate that those who didn't exercise. This process can be compared to building new railways between distanced cities. But there are a few catches. 1. The training has to be intensive enough. 2. Just weightlifting or just running is not enough. You have to understand the difference between IGF-1 and BDNF growth factors. Exercise has been long known for promoting neurogenesis, the growth of new neurons. But newer studies have also demonstrated the ability by which exercise influences on the molecular system. The forming of new pathways in brain is called a synaptic plasticity, and it enhances learning and memorization. We know that intensive and regular physical activity is modulating energy metabolism, but what is overlooked is that plays a critical role with the brain-derived neurotrophic factor system, BDNF. Well, that one is secreted more in cardio than weightlifting, but we'll get to that later. Let us start with the second postulate. Newer studies have shown that particular high-intensity regular training, in contrary of old doctrine of prolonged cardio, produces remarkable changes in peripheral levels of BDNF and catecholamine as dopamine, epinephrine or norepinephrine. One study has demonstrated 20% faster vocabulary after intense exercise with simultaneously better short and long-term retentions of the novel vocabulary. Furthermore, exercise increases, in some cases almost double, the survival of newborn cells, suggesting that physical activity is one of the best methods to promote neurogenesis. How does this happen? Exercise increases neuronal metabolic and mitochondrial functioning, and the efficiency of its machinery decreases hippocampal-related oxidative stress. The most obvious is the process of generating new hippocampal neurotrophins. Those are a family of growth factors that induce the survival, development, and function of neurons, between which the BDNF is the most prominent. By upregulating the levels of BDNF, with help of IGF-1, and supporting hormones testosterone versus estrogen, exercise induces both neurogenesis and neuroplasticity. The crucial process regarding learning is called long-term potentiation, LTP. The neurons communicate with each other through axons which end as synapses. When one receives a certain level of excitation, it triggers an action potential which jumps, with help of neurotransmitters, through synapse to another neuron, where producing excitatory or inhibitory response. LTP has simplified the process of enhancing firing from neuron A to neuron B. In reality, this is a bit more complicated, since LTP works also by increasing the input specificity. One synapse does not spread to other synapses, cooperation between synapses and simultaneous strengthening of several weak signals. Studies have shown that combining aerobic and resistance training, simultaneously as circuit training or high-intensity interval training, exerts the greatest benefits to cognitive processing. The richer the exercise regimen will be, the sharper your mind will become. But how exercise influences the brain differs also from the type of exercise you are engaged in. Resistance and cardio training have showed the greatest results, although they are acting through completely different pathways. Cardio tends to have a greater influence on vascular processes and BDNF, while resistance training influence IGF-1 and other supporting hormones. The highest effect are to be produced by mixed-type regimens. There are two more benefits of regular exercise. First, it helps to regulate cortisol levels and stress response, which have been linked multiple times to impaired cognitive functioning, but as well as physical damage to hippocampus. Through activating amygdala-enhanced memory formation, since emotionally salient information are stored more efficiently. Secondly, it asserts significant protection against Alzheimer's disease and dementia. Most scientists agree that beta amyloids, the non-pathogenic second level of the protein structure, somehow starts to clump together, interfering and distorting the normal neural network. It is still unknown if the excessive aggregation of its plaques or some other culprit is to blame for oligomers, dysfunction of cytoskeleton proteins, diabetes. Furthermore, this optimizations also exert a notable neuroprotection to our brain as we are getting older. It is comparable to intensive mental work, like learning a new language. Vigorous training regimen has been found extremely beneficial in an Alzheimer's model by increasing flow of brain fluid, CSF, and cleaning neuronal structures. Completely different benefits are being asserted in Parkinson's disease, where dopamine-producing cells are lost, but only at first glance. In studies, intensive resistance training has helped to restore impaired motor circles and neuronal differentiation, decreases loss of dopaminergic cells and increase transfer of dopamine-producing cells to damaged regions. It is speculated that exercise in Parkinson's is doing similar thing, while in Alzheimer's cerebrospinal fluid is washing off amyloids beta. In Parkinson's the enhanced cleansing mechanism is diminishing alpha-synuclein, another protein that aggregates and causing death of neurons.